Hey, welcome back, class. Today's lesson is about elastic potential energy. So, the only kind of potential energy that we've studied so far is gravitational potential energy. That's the energy that something gets based on how high off the ground it is. It has the potential to fall back down. Well, as you can imagine, in a spring, if you compress a spring, there's some potential energy stored in that spring that will be released as the spring comes back to its original shape. Or if you stretch a spring and it comes back to its original shape, that's also potential energy. Those are elastic potential energy. The potential energy of something that is stretched or compressed when it springs back. So we have to come up with an expression for that. Let's see. Well, we know that what we have about springs so far is the force. Let me just see what I got here. How about just plain old black? That ought to do it. Oh, that's pretty funny looking. How about that? Force is equal to kx, where k is the spring constant. So you may remember that with gravitational potential energy, the work done to lift something up is equal to the change in gravitational potential energy. And work, remember, is equal to force times displacement, which we use as s or x. Okay, so let me do it this way. I'll call it Fx. So if we take the force multiplied by the distance traveled, that's going to give us the amount of work done on the spring, and therefore the amount of elastic potential energy stored in the spring. So if we had a graph, and say this axis is F, and this axis is F. Remember, F equals Kx. Okay, that's going to look like a line like this. Okay, F equals Kx. So K is the slope. And so if we traveled, say, a distance x, so this distance is x from here to here, this height is going to be the force at that distance, which is kx, and the work done is going to be the area under this curve, because it's f times x, which is kind of like the integral, or the area under the f of x curve. Okay, so area equals work. Okay, well that's equal to 1/2 base times height, since it's a triangle. So that's 1/2 times x times kx, or 1/2 kx squared. Okay, so that's going to be equal to the potential energy, the elastic potential energy. So that's your big equation for this section. Okay. Now I always like to show the calculus people where calculus might come into it. Okay, so you know what? I'm going to make this line just a little bit finer, because it's getting to be a bit much here. So the area under that curve is going to be the integral of f of x dx. That's the integral of kx dx. Well, you may remember that you raise the exponent from 1 to 2 and then divide by it, so that's 1/2 kx squared. So it all works together, and that's kind of neat. That's the whole deal. Okay, well maybe, let's see, can I come up a little more? I guess not. So let's do a new piece of paper. Okay, so I've made a new page, and let's see what we've got here. We know F equals kx. Potential energy, elastic potential energy is 1/2 kx squared. Now, total mechanical energy is kinetic energy plus gravitational potential energy plus elastic potential energy. So it's 1/2 mv squared plus mgh plus 1/2 kx squared. And then we have that E initial equals E final. Let's see, can I get rid of that thing? I guess I'll just pull it out of the way. Let's see a way to get rid of it. Hold on a minute. Okay, so let's try to use this information to actually solve a problem. Hold on, let me pull this thing up, because what we really just need is this much. Okay, so let's go to page 295, example 7. Okay, let's have a look at this. 295, example 7. Figure 1018 shows an object of mass m equals 0.200 kilograms. Okay, so let's put what we are given. M equals 0.200 kilograms. Okay. It is vibrating on a horizontal frictionless table. The spring has a spring constant of K equal to 545 newtons per meter. Okay. Spring is stretched initially to x0 equals 4.50 centimeters. Okay, so if we're going to convert that to meters, we move the decimal place 2 to the left, equals 0.0450 meters. It is then released from rest. Determine the final translational speed, Vf, of the object when the final displacement is, okay, so we have an A and a B. So x sub f A equals 2.25 centimeters, which is 0.025 meters, and x sub f B equals 0 centimeters, which of course is 0 meters. Alright, so basically what this is going to come down to is a simple matter of initial energy equals final energy. So initially we have a mass that's not moving. We've got V initial is 0, so we can also say that V0 equals 0, and the string is stretched this much. So all we have for our energy, E initial, is equal to just the spring energy, 1/2 kx squared. 1/2 times 545 times 0.0450 squared. And if we calculate that out, that is going to be 0.552 joules. That's our initial energy. Now we got two cases. Let's calculate our final energy under A. Okay, so E final A. Okay, now it's moving, so it has kinetic energy. We're assuming because we've let go of it, right? And it's gone from 4.5 centimeters down to 2.2 centimeters, so it's springing back in towards itself. So we've got the kinetic energy, 1/2 mv squared, 1/2 times 0.200 times V final A squared plus whatever elastic potential energy is left, right? Because it's still stretched a little bit. So that's 1/2 times K, which is 545, times the new X, which is going to be 0.025 squared. So let's see. What do we got there? We've got to basically calculate. We're solving now for this V here. Okay, so I've done a little bit of calculation here, and we end up with this piece here is going to be, let's see, maybe I'll grab a calculator just to be careful. Hold on. Okay, so half of 0.2 is 0.1, 0.1 V final A squared plus, and this thing over here turns out to be 0.138. But, so that's final energy, right? But that has to equal initial energy. So therefore that's equal to 0.552. So let's subtract 0.138 from both sides. And we get 0.1 VFA squared equals, let's see, 0.414. 0.414. Divide both sides by 0.1. And we get that V final A squared equals 4.14. So V final A equals the square root of 4.14, which is equal to 2.03 meters per second. All right. There's our solution to part A. How about part B? Okay, we're running out of room here, I believe. I don't think this thing's going to let me slide up anymore. Nope. So what am I going to do? I'm going to do B over here, if you don't mind. Okay, so here's part B. Sorry about that. But let's see. Part B is similar, only when we get to part B, let's see what we have here. We've got, hold on, 0 centimeters. Okay, so that means that there is no elastic potential energy. We've taken all of that initial elastic potential energy and we've converted it all into kinetic energy. So that means that our kinetic energy, which is just 1/2 m, which is 0.200 V final B squared has to equal this initial elastic energy, which was 0.552. Okay, so 0.1 V final B squared equals 0.552. Divide both sides by 0.1, and V final B squared is equal to 5.52. So V final B is the square root of 5.52, which is equal to 2.35 meters per second. So there's our answer for B. And that's the whole problem. So to review, we're basically just saying that the initial energy is equal to the final energy, and in each case the energy is equal to the kinetic energy plus the gravitational potential energy, which doesn't come into this problem at all, plus the elastic potential energy. So it's 1/2 mv squared for the kinetic, mgh, which didn't come into this problem since it was on a horizontal table, and 1/2 kx squared. So let's see, let's try another problem from the book. Okay, so if we go to page 297, example 9, we can look at the picture on the right there, figure 10.2, and at one point they're holding the spring, this mass on a spring up, and then they let go and let it fall. And it falls down, and then it comes to a stop, right? Its velocity decreases because the spring is catching it, and then it starts bouncing back up. And they want to know how far down does it go before it starts bouncing back up. Let's see what we have here. A 0.2 kilogram ball, m equals 0.2 kilograms, 20, is attached to a vertical spring, as in figure 10.20. The spring constant of the spring, K, is equal to 28 newtons per meter. The ball is supported initially so that the spring is neither stretched nor compressed, is released from rest in the absence of air resistance. How far does the ball fall before being brought to a momentary stop by the spring? So you let go of that ball, and it's going to fall downward, then it's going to bounce back up, and it's going to do simple harmonic motion, right? Up and down, up and down. It would be tempting to think that when it got to that bottom, we would have gravitational force pulling down, spring force pulling up, and by equilibrium we could set our vertical forces equal. But that would assume there was no acceleration, where in fact at the extreme end of simple harmonic motion the acceleration is maximized. So that's not going to work. Instead we got to look at potential energy. Okay, so initially, what's our potential energy? Well, it's mgh, right? Mass times gravitational acceleration times whatever height it's at. That's got to be equal to, now, when it gets to the bottom, it's still not moving, so there's still no kinetic energy, neither in the beginning nor in the end. But now the string is stretched, so that's got to equal 1/2 kx squared, or k, let me just get rid of that for a second, 1/2 kh squared, because h is the distance that it falls. Okay, and so now it's lost all that gravitational potential energy. That energy has all been absorbed by the spring, been converted into elastic potential energy. There's no kinetic energy because in both cases it's not moving. It moves in between, but here it's not moving and it comes to a stop here before it bounces back up. So we're asked to find h. Well, let's see. All we have to do is plug a few numbers in. 0.20 times 9.8 times h equals 0.5 times 0. Oh no, it's going to be times 28 times h squared. Okay, let's see. 0.2 times 9.8. Let me just do that on my calculator quickly. 0.2 times 9.8. That's 1.96. 1.96h equals 0.5 times 28. That's 14 h squared. Okay, so if we want to get h by itself, we could divide both sides by 14h. That h cancels. Those 14's cancel. This h cancels this 2, making it into a 1. H squared over h is h. So 1.96 divided by 14 is 0.14. So we have 0.14 equals h, and that's meters. That's a solution. So it's not really too hard. I'm not going to give you a problem to do at home here because we'll do some problems in class. But basically all we're doing is we're looking at initial total energy equals final total energy. In this case, we start out with gravitational potential energy, we end up with elastic potential energy or spring potential energy. In this case here, we started out in the first one. Let's see, we got kind of a mess here. Let me just close this up for a second. In the first case, what we had was we started out, let's see, with some spring potential energy because the spring was stretched, but there was not moving, so there was no kinetic energy. Then the spring was let go for a little bit, and we can see that we lost some of the spring potential energy, but we gained some kinetic energy because it started moving, so we had to set those equal. In the final B version, we got back to 0 centimeters, so we had no elastic potential energy left, nothing but the kinetic energy. And so we just set the energies equal, and that was the end of that. So our biggest point here is that the elastic potential energy is 1/2 kx squared, and you just treat it like the other gravitational potential energy and the kinetic energy. They're just energies. It's like a bookkeeping system. As long as you realize that energy is not created or destroyed in a closed system, it's just converted from one form to another. So if you lose some spring energy, maybe you gain some kinetic energy. I mean some gravitational energy, maybe you gain some kinetic energy, maybe you gain some spring energy. It has to be juggled back between these three, and we'll learn over time other kinds of potential energy that it could be converted into. And that's all I've got for you today.